So good evening everyone, and are there any queries from the previous session? We'll do a brief recap of what we did in the previous session and then we'll move on to the topics to be covered in this week, that are maximum likelihood estimation and logistic regression. So let us go to the previous week's topic. So in the previous week we saw linear regression and its applications. So basically we saw what linear regression is used for. So there were like basically two use cases. First was to estimate a linear relationship between the independent variables and the dependent variables. For example, like sales in ice cream, or like for example TV ads and the sales of product. So yeah, we given the data points, we were trying to find a linear curve that fits the best, like trying to find the best fit for the given data points, and then using any unknown value we can estimate or predict the corresponding dependent value for that variable. And in that case we saw like the least square method, which we use to fit the linear model. Okay, let me just share it on iPad so that it is easy for everyone to understand, and then we'll quickly move on to maximum likelihood estimation. Okay, I hope my iPad screen is visible. So in the linear regression we had been given a independent variable and a dependent variable, and then the task was, given the data points, we had to fit a line that minimizes certain objective, and this objective was the least square function that we were trying to minimize. Okay, so this was the case of single variable, like one independent variable. Then we moved on to multiple regression, wherein you have multiple independent variable. I think we did not discuss it in detail, so let me just quickly discuss that. So in the case of multiple regression, we have two or more than two independent variable. Say you want to do some weather forecasting, and you have some independent variable 1 and 2, and you want to see if it will rain or not. So let's say this one independent variable is temperature, and another independent variable, let's say wind speed, just an hypothetical example. So based on this, you have been given this x1 values and x2 values, and you want to predict the amount of rain it will be there on that particular day, which will be, say, in mm. So I have been given certain data points collected over time. So for this particular x1 value and this, so this is x1 over here, and this is x2, and this is the corresponding y value. Okay, so in the case of this three-dimensional space, we are trying to fit a plane, and the equation of this plane is y equal to beta 1x. So let us use b1, b2 and b3. Okay, so in the case of linear regression, we had this equation y equal to b1 plus b2x which represents equation of line. As you increase the number of independent variable, the dimension of the space in which you want to find the relation, it also increases. So in this case we had two independent variable, so the dimension of the space is 3, and what we are trying to find over here is the equation of the plane. So here in this case there are certain terminologies associated with it. So the dependent variable y is known as response variable, and this surface that you are getting by this equation b1x plus b2x plus b3, where b3 is the constant, this is called as response surface. So given the value of x1 and x2, you have to predict what is the value of y. Generally it is given as y hat. Y is nothing but the actual value and y hat is the predicted value. Okay, so this was all about multiple regression, and the method is similar to what we did in the linear regression case. We will see one example in Python. I'll check if I have any. Yeah, I might be having one example in Python notebook, so we'll see that quickly later. Is it clear about multiple regression? We'll move on to logistic. We'll move on to maximum likelihood estimation, logistic regression in this week. So before that, let me see if any of the topics is left. Okay, so let us quickly do the recap of this Python notebook. Okay, somebody's here. Okay, so I'll skip this two-way ANOVA part. So in the previous class, we saw one example of TV ads and car sales. Okay, so we had this data in regression.excel file. Only 5 data points were there, and then we were trying to fit a line on this data point. So this is just a scatter plot of the same, and I think some of one of the persons asked like doubt regarding how to save the figure. So the command to save it, or the function to save the figure, is plt.savefig. Request everyone to be on mute. Any query?
Satish, we are unable to see your system.
Oh, sorry. Let me resume my presentation. Sorry.
Yeah.
Okay, I hope it is visible now. So
Yes.
yes, so we are reading data from the regression.excel file, which had these data points, TV ads and car sales. These are the independent variables, and these are the dependent variables values. So what we were trying to do, we were trying to put a scatter plot which represent the independent variable and the associated dependent variable over here, and the aim is to fit a line to this data points. Okay, and then there was a query like how to save the plot. So you will have to use this function plt.savefig to save this particular plot over here, but you will have to have this plt.show which displays the plot in the environment after savefig, because if you do it before savefig, it kind of like instantiates a new figure, as somebody rightly pointed out in the previous session. So you'll have to make sure that plt.savefig is always written before this plt.show. I have added some comments over here for you to refer to, so you can refer to this notebook later whenever you are free and play around with it. Okay, so then we had this independent variable and dependent variables in different lists, and then we added this constant over here. So what is the reason of adding this constant? Let me just show it on iPad. Okay, so we have this line equation y equal to b1 or b0 plus b1x. So let us say we have these data points x1 y1, x2 y2, x3 y3 and so on up to x and y. Now if you substitute these values in this equation, so it will be y1 equal to beta naught plus beta 1a. Let us consider this as beta because these are the population parameter. You will have to remember that b1 b0 b1, so this alphabetical notations are used for the estimated parameters, and these Roman alphabets like sorry Greek letters are used for request everyone to keep their videos off. Okay, so these Greek alphabets are used for population parameters in this case. So the assumption over here is that these data points are coming from the population, and we are trying to fit a line which best represents the uh, relation between the independent variable and dependent variable at the population level. So these are the estimates. B0 and B1 are the estimates, and we try to find the significance of each of these variables in the case of multiple regression as well. We'll come to that later. So the reason for adding a constant over there in this particular equation in Python notebook, so let us say y1 equal to beta naught plus beta 1 x1, y2 equal to beta naught plus beta 2 x2 and so on, yn equal to beta naught plus beta n xn. If you write it as a matrix, can someone tell me how will be the matrix formulation of this particular set of equations or vectorization? If I want to write the same thing as vectors, product of vectors, this particular thing, how can I write that? Anyone? Any guess? Okay, let me write it over here. Y1 equal to, let's say B1 x1 plus beta naught let us consider only these three equations. So I want to write this as a product of two vectors. So how can I do that? Yes, matrix. So what will be the matrix? Like you have to define two matrices over here. Yes, I'll share the collab link, Saravanan. Like I'll put this in the drive folder, and you can find the drive folder link on like below my like in the YouTube video description where I'll be uploading all these recordings. I'll share it over here in chat as well. Okay, so let me just share it. So you can write it as x1 1, x2 1, x3 1 multiplied by, sorry, this is beta 1 not beta 2 beta 3. So if you simplify this, you will end up getting this particular equation. So now is it clear like why we add this constant? So that constant that is getting added in the Python code, it's for this reason. So we want this y-intercept value to be there. So we have been given this vector y or list y, we have been given this list of x. So what we are doing, we are just appending this constant 1 to the independent variable list and then passing it on to the OLS function. So let us go back to the Python code. Okay, so here we are. So the TV ads was like 1 2 3 4 1 2 1 3 2 1 3, and we were adding this. So this sm dot add constant function will add ones to your particular independent variable list, and then you are passing this in the OLS function. OLS is nothing but ordinary least square. So you pass in the value of y and the x, which is appended with constants, to this OLS. You fit the data to the model, and then we are printing the summary over here. So this summary contains multiple information. One is r square over here, which represents the amount of variation or the variability in the data that is explained by this particular regression equation or regression model. And there is this term called adjusted r square. We'll come to it shortly. And here are the estimates of the parameters, the constant and the coefficient of the independent variable. So are there any queries relating to this?
Saish, this is program for simple linear regression,
Yeah,
right?
this
Not
is
for multi.
this is for simple linear regression because there is only one independent variable over here. Yeah,
Correct.
but similar can be applied for multiple regression. We'll come to that in the next in another notebook. I have one more notebook, so we'll discuss that in.
Sure.
Yeah.
Understood. Yeah.
So here r square is the it is known as coefficient of determination, as we discussed in the previous session. So what we are trying to say over here is, like, it says that 87.7 like the percent of variability in the data is explained by this line that is fit on the data given these data points. Okay, and adjusted r square. Okay, let me just go to slides by Professor Ramesh. I'll explain it over there. Okay, here it is. Is it visible to everyone? So what was our r square? R square was SSR by SST. SSR was sum of square due to regression. That is the amount of variance that was explained when we were adding this independent variable, when we were taking this independent variable into consideration, and the total sum of squares without the independent variable. Okay, so the amount of variability that is shown by this particular independent variable, addition of independent variable, is added by this r square. But in the case of multiple regression, you have multiple independent variables, right? So as you increase the number of independent variables, the chances are that your models, the predicted line or the regression model, it kind of like makes less prediction errors as stated over here. So this SSE, that is sum of square due to error, it will decrease, and which will eventually increase the sum of square due to regression, which will eventually increase this r square value. Okay, but in statistics, to avoid any overestimation of this parameter r square, we kind of normalize it with respect to the degrees of freedom, sorry, not degrees of freedom, the number of independent variables. So this is the formula that is used for adjusted r square. So here you can see there is this term p, which represents the number of independent variables. So as you increase the number of independent variables, this particular r square value that you have computed, you kind of like trying to have an estimate of it, which is taking the number of independent variables also into consideration. Okay, So as we saw in the previous session, the value of r square can range between, so what is the answer? What will be the values of r square? What values can r square take? Anyone? We saw it in the previous class, right? Like you can answer in the chat or just unmute yourself and answer. Yes. What values can r square take? Anyone? It's okay if you make mistakes, we'll revise it if you forgot it, but yeah, just try to answer. Okay. Yes, Bharat, you want to answer? Or you have any query? Okay, so let us see, like the value of r square is always positive and it will range from 0 to 1. How? SSR is SST minus SSE. When the error is 0, SSR is equal to SST, and in that case r square value will be 1. But when the error is like there is when SSR is 0, so r square value, like there is complete error, like error, this complete error is equal to the total error. So in that case SSR will be 0 and eventually r square will end up being 0. So r square can range from 0 to 1. But that's not the case with adjusted r square. It can also be negative in certain cases. When I leave that question to you, like you can answer, you can think over it and then see for what values of r square this adjusted r square is going to be negative. Okay, so let us move on to the other part of it. Just a second, let me just check if anything else is missed over here. Okay, so we saw r square, we saw adjusted r square, which takes the independent variable, number of independent variables into consideration, and F statistic over here. So this F statistic is nothing but sum of squares due to error, sorry, sum of square due to regression divided by like sum of square due to error or mean sum of squares. So it kind of gives you and statistical significance of the overall model, if the overall model is statistically significant or not. So higher the F value, lower will be the probability, that is the associated p value, and more will be the more will be the significance of the model. And then for every single variable over here, like in this case we had only one independent variable, so there will be like associated t value that we can compute. We saw it in the previous session, so I am not going to into the details of it, just doing a recap of it, what we saw. And then for every independent variable, we were having the corresponding p value to identify if the particular estimate of the independent, the coefficient of the independent variable is significant or not. And then we saw one more example. Okay, so I'll leave it over here. We'll move on to maximum likelihood estimate, and then followed by logistic regression in today's session. So let me share my iPad screen. Okay, so does anyone have any idea like what maximum likelihood estimate does? Anyone? Okay, let us see. Let us say you have few data points over here. And I try to fit say normal distribution. One normal distribution is like this, another normal distribution is like this, and let's say like this. So which distribution do you think will best represent the given data points? I have these blue colored data points and I'm trying to fit these normal distributions. Each distribution is having its mean and the standard deviation, which are nothing but the parameters of the distribution. So which one do you think will be the best fit for the data points? Okay, someone says green. What about the others? What do you think, like which one is the best fit for the particular data points? And we'll formally see this. Okay, someone says red. What about the others? What do you think will be the best fit? Okay, okay. Because of most of the distribution, it is positive. Okay, let us now see like the correct interpretation of this. So the correct answer is red over here. So why? The equation for the formula for normal distribution is given as 1 over root 2 pi sigma square e to the power x minus mu square upon 2 sigma square. So let us consider this mu 1 and sigma 1. So what will be the corresponding, so this points over here are the probability densities of these data points. So this, let's say this is x1, x2, x3 and so on up to xn. So this particular point over here with respect to this red curve, which is having mu1 and sigma 1 as parameters, it will be 1 over root 2 pi sigma 1 square, sorry, e to the power x1 minus mu1 square upon 2 sigma square. Okay. Similarly, for this point it will be x2, for this point it will be x3 over here, for this point it will be x4 and so on. Let us denote it by pi for ith point, xi minus mu1 upon 2 sigma 1 square. Okay. So I want to find a distribution that maximizes the likelihood. So this particular point expression over here is called likelihood. That is the probability of xi given the parameters of the distribution. Okay. So to maximize, I want to find a distribution that maximizes the likelihood of each of the data points. Okay. That distribution will be the best distribution that can fit my data. So in this case, you can see that it is the red curve which will be having higher likelihood values for the given data points. And how to formally state this? So if I want to maximize the likelihood of all the data points, which means that I want to maximize P1, I want to maximize P2, P3 and so on up to Pn, which is equivalent to maximizing their product. Assuming all these data points are independent. Okay, let us denote this by L. So till this point, is it clear? Like we want to maximize the likelihood of each data point with respect to the distribution, and maximizing the likelihood of each data point is equivalent to maximizing the product of their likelihood. Is this part clear, or please let me know like if it is not clear, I'll explain it to you again. Yes, no, anyone? Okay, let me just give you an example. Let's say likelihood values are, or let's say there are 3 values. I have this histogram 2, 3, 2 and this histogram. So if you take the product of these values over here, 2 into 3 into 2, and over here 1 into 2 into 1. So which one is higher? Obviously this one, right? Here the probability or value, not the probability, but the value of each of this random variable is higher let us not consider that, like just consider it as values only. I just wanted to give some intuition behind like why we consider the product of this particular probability values. So here the product of these values is definitely higher than this particular values. So what we are trying to do here, so if you see the values over here on the with respect to the red curve and with respect to the green curves and yellow curve, so product of all these values on the red curve will definitely be higher compared to the products of values with respect to the green curve or yellow curve for these given data points. So that's the intuition behind it. So we want to find a distribution which maximizes the probability of the data points, the product of the likelihoods of data points, okay, which is nothing but 1 by root 2 pi sigma 1 square, or let's say sigma in general, e to the power x1 minus mu square upon 2 sigma square into 1 by root 2 pi sigma square e to the power x2 minus mu square upon 2 sigma square, and so on up to xn minus mu square upon 2 sigma square. So this is the product. Now solving this is a tricky task. To see if some variable is getting maximized, some variable is getting maximized, the general method that we follow is differentiate it with respect to the independent variable and equate it to 0. Similarly for the standard deviation, but to make it easy, we generally take log of this particular product. Why? Because it becomes summation of the logs of each of the likelihood, which is easier to solve. So if you take the summation of this, if you take the log of this particular product over here, and differentiate with respect to the mean and the standard deviation and equate them to 0, you will get an equation for mean and standard deviation, and that particular estimate will be the maximum likelihood estimate for mean and the standard deviation. Okay, let me show this to you in Professor Ramesh's slides, where he has used it for different distributions. It's not just for normal distribution, but you can use any distribution, let's say Poisson distribution. So what is the formula probability density function, probability mass function for Poisson distribution? Does anyone remember? We saw it in one of the previous sessions. Probability of x given lambda is, you can unmute yourself and answer. Okay, it is e to the power minus lambda, lambda to the power x upon x factorial. So we have been given the data points x1, x2, x3 up to xn, and we want to find lambda which maximizes or which best fits these data points or maximizes the likelihood of each of the data point. Okay, so let us see these examples, solved examples in Professor Ramesh's slides, and then we'll move on to certain questions. So here are the example. The first example was for the Bernoulli distribution. So Bernoulli distribution is nothing but product of probability values. Like say you have been given say 10 n random variable, and each random variable will be having a certain probability of success or failure. Okay, so you have been given so probability of a particular random variable is given by p, and the value, if the random variable takes the value 1, the probability will be p, and if it is 0, then probability will be 1 minus p. So in this question, what is given, there are 10 new bike helmets manufactured by certain company, and upon testing it was found that the first, third and the 10th helmet are flawed, whereas the others are not. So x1, x3 and x10 are flawed ones. So the probability of being flawed is p over here, and the rest of them are not flawed. So the product will be p into 1 minus p. Third one is having fault, it's p. Okay, let me show it on iPad quickly. I have 10 helmets, and it is given that the first, third and the 10th one are having some flaw, and the probability of the helmet being flawed is p. So the probability of it the helmet not being flawed is 1 minus p. So the likelihood of this particular data points will be p into 1 minus p into p and so on into 1 minus p, which is nothing but p to the power 3 1 minus p to the power 7. So you want to find the value of p which maximizes this entire product. So the simple way is to differentiate this with respect to p and equate it to 0. You will get a particular value of p over here. Similarly, for other distributions as well, given the value of data points, you substitute that value in the formula for that distribution and then take a product of all the data points, take the log of it to convert it into sum, differentiate with respect to the independent variables, the parameters, unknown parameters, and then equate it to 0 to find the estimates of the parameters with respect to the data points that you have. So in this slide, in this particular example, for the Bernoulli example, the task was to find the value of p. Same thing can be like in this case, we were knowing that the first, third, and the 10th helmet were flawed. But let's say we don't know the which 3 ones. There are 3 flawed helmets in the particular set of helmets, and we don't know which ones are flawed. So there are possibilities of any 3 helmets being flawed. So in that case, we go on to binomial distribution, and we also saw it in one of the previous classes. So how it can be solved? Similar to what we did over here in the Bernoulli distribution. In this case, we will have this extra term, that is the combination. Out of the 10 helmets, you are choosing 3 helmets that are flawed, and the probability of being flawed is p. So it will be 10c3 p to the power 3 1 minus p to the power 7. It can be generalized to any value, 10 ncx p to the power x 1 minus p to the power 10 minus x. Now you want to find the value of p over here. You have been given the values of these data points x1, x2, x3 up to xn. You have to substitute them over here, take the product of the values and differentiate with respect to p and equate it to 0 to get the value of p that best fits the particular data points. Okay, you are trying to find a binomial distribution that best fits the given set of data points. Similarly, there are other examples for Poisson distribution and normal distribution and exponential distribution. So please try this out on your own. I'm not going to go into the details. Okay, so we'll see some questions that you might expect in your examination. Okay, so in the previous session we missed some of the questions. So there was this question: a variable that takes on the values of 0 and 1 and is used to consider the effect of qualitative variable in a regression model is called. We can answer this, and then we'll see what is the application of this variable.
Dummy variable.
Yes, that's the correct answer. So dummy variable, why it is called dummy variable? So let me explain it to you. So there was an example given in the lectures by Professor Ramesh. So he talked about the, I think it was like delivery time or taken. So it was like miles covered. I'm not very sure about exactly the. So let's say there was one variable x1. So it was having some numerical values, say 1 to 500 and 220 and so on. and there was one categorical variable, say electrical, mechanical, and so on, and there was a dependent variable. So these two are the independent variables, and this is the dependent variable. Let's say amount, some amount, 200, 550, and so on. So given these two independent variables, I want to predict what will be the y value. But in this case, the problem is that this variable is categorical in nature. So I want to convert this particular variable into numerical value. And how many variables I have? Like I only have two categorical variables over here, like two possible values, electrical and mechanical. So I can represent this as 1 when if it is electrical, and 0 if it is mechanical. So now I have converted this to numerical value, and then I can fit a regression model on top of this particular data. So this particular variable is called as dummy variable, because you are kind of like trying to replace this particular categorical variables with these zeros and ones. So if there were like more than 3 variables, let's say A, B, and C, or let's say blue, black, these are some hypothetical variables, value, and red. So what will be the dummy variables in this case? Say x1 is having certain values, x2 is having either blue, black, or red, and there is a dependent variable. So if you want to find associate some values with this particular variable x2, so what will be the possible values? Will 0 and 1 suffice, like just 1 0 and 1 1? Any answer on this? Any thoughts? I have some numerical value over here, and I want to convert this categorical variable into some numerical representation using zeros and ones. So will a single 0 and 1 be sufficient to represent these values? That's the question.
No.
Okay, so what will be the possibility, like what can be done over here?
0, 1 and
No,
2.
I think that will be sufficient.
Okay, let's say 0 represents blue and 1 represents black. So how will you represent red? Yes, that is correct, Sir Anand. So you need two variables in this case. So we can use two values over here. Let's say 0 1 represents blue, 1 0 represents black, and the absence of both the variables represents red. So here we were having 3 categorical variables, and in that case we use 2 dummy variables. Okay. So let's say we have one more variable, pink. So how many values, like what will be the value? So in this case we will have to use 3 dummy variables. Blue will be 0 0 1, black will be 0 1 0, red will be 1 0 0, and absence of all these things will be represented for pink. So you have x1 certain values. So let's say this is x21, x22, and x23. So now you have 4 variables and one independent variables and one dependent variable. So you can fit a multiple regression model on top of this independent variables. Is it clear to everyone? Soumitra, is it clear? Yeah. So if I have n independent variable, I will have n minus 1 dummy variables. N categorical variables, not independent, n categorical variables. I can represent that n categorical variables using n minus 1 dummy variables. Okay, so let us go back to slides. So a variable that takes value of 0 or 1 and is used to consider the effect of qualitative variable in a regression model is called dummy variable. And yeah, we saw this one. So multiple regression is the model which is having more than one independent variable. In multiple regression, the error term epsilon is assumed to have, does anyone know the answer to this? Okay, one person answered. Yeah, so the correct answer is mean 0. So the error term that you get, that is the actual value minus the predicted value. This is the error associated with each of the predictions. So if you take all these error values and fit a distribution on top of it, normal distribution, you will see that the mean is close to 0. For the population, mean is 0 and some standard deviation sigma. So this error term is assumed to be normally distributed for the regression model or linear, in the case of linear regression or multiple regression. And we saw this as well in the previous class. Okay, this is one question. The ratio MSE upon MSR yields think over it. Okay, what about the others? What do you think is the answer? Okay, let us move ahead. So the correct answer is none of the above. The correct F statistic formula will be MSR divided by MSE. We saw it in the previous session. So you have to be very careful over here in this case. MSR by MSE is F statistic, but this particular ratio has no meaning. So the answer is none of the above. Okay, in a multiple regression analysis, SSR is equal to 1000, SSE is equal to 200. The F statistic for this model will be answer for this. Yes. Yeah, that's right. What about others? Is everyone getting what is being covered in the sessions? Yeah, please let me know. Like these sessions are made to cover your doubts, queries relating to the course. So if you are not understanding, please let me know. Like please feel free to ask your queries. Okay. So yeah, as one of you mentioned, there is not sufficient information available over here. The correct answer for F statistic will be MSR by MSC, and MSR is SSR divided by degrees of freedom for SSR, and MSC divided SSC MSC will be SSC divided by degrees of freedom for SSC. So SSR and SSC values are given to you, but the degree of freedom, the corresponding degrees of freedom are not given. So in that case, the correct answer will be not enough information is provided to answer this. Okay. So let us go to this week's problems. We will see logistic regression. First we will see like some problems on maximum likelihood estimation, and then we'll move on to logistic regression, and we'll solve some problems in Python. Okay, so I added this Z table over here just for those like who might be having query relating to how to find the p value for a given Z value. So in the one sample test, like we saw how to compute the Z statistic or Z test. So once you get the Z value, say you got the Z value of 0.75, so or 1.65, so you can go to 1.6 over here and 0.05 over here. The intersection of these two particular values over here will give you the p value corresponding to the value 1.65, which is nothing but not p value, sorry, the CDF, the area under the curve till that particular point. So p value will be nothing but 1 minus this particular CDF value that you will be getting using this Z value. Okay, so similarly in the case of T table, you will be having a one more information, degrees of freedom. So given the T value and the degrees of freedom, you will be having particular CDF associated with it, and then to compute p value depending on whether it is a one tail test or like upper tail test, lower tail test or two tail test, you will have to compute the p values accordingly, and we saw it in the previous sessions. So I'll leave it over here, but this was just to clarify. There was one query in some sessions like how to compute this score like the CDF using this Z table. So this is an answer to that query. Okay, so coming to a maximum likelihood estimation question, state true or false. Maximum likelihood estimation is a method to find most likely density function that would have generated the data. Is it true or false? Okay, let me start a poll and you answer via the poll. Don't answer in the chat. Okay, I launched a poll, so you can answer your you can answer via the poll. Okay, just want to encourage everyone to answer. That's why I have started the poll. So it's anonymous. So even if you make mistakes, it's not getting recorded over here. So please feel free to answer. Maximum likelihood estimation is a method to find most likely density function that would have generated the data, and we just saw it in sometimes back. Okay, only one answer so far. What about the others? Okay, let us see the answer. So the answer is true. Let me quickly recap what we saw just now. So what maximum likelihood estimation does? Given the set of data points, everyone please be on mute. Yeah, so given the set of data points, you are trying to fit in a distribution, any distribution, let's say normal distribution, which maximizes the likelihood of each of the data points. See, this was one distribution, this is another distribution. So which of these two distribution fits the data points in a proper way, or best fits the data points? So this is the red one, because if you see the values, the density values over here, it is, if you take the product of these values, P1, P2, P3 and so on up to Pn, and with respect to this green data points, P1, P2, P3 up to Pn, sorry. So if you take the product of this, so which one will be higher? Obviously this particular product with respect to the red curve. So you are trying to find a distribution with unknown parameters. In this case it is sigma and mu for normal distribution. For Poisson distribution it is lambda, for binomial distribution it is p, for one-order distribution it is p, for exponential distribution again it is lambda or mu. The notations might change in literature. So these are the unknown parameters that you have to estimate given the data points. And what is the aim? You have to fit the distribution such that the likelihood of each point with respect to the data, the distribution is maximized, and which is denoted by this function P1 P2 into Pn, that is the product of the likelihoods. So whatever distribution you have with parameters theta 1, theta 2 up to theta n, whatever unknown parameters, so the probability of this x1, x2, x3 up to xn, given these distribution parameters, I want it to be maximum with respect to these data points, and this will be maximum for so given any other distribution parameters prime, theta 1 prime, theta 2 prime up to theta n prime. So in this case, this was the parameters of this red distribution were sigma 1, sigma mu 1, and for the green one mu 2, sigma 2. So probability of x1, x2 up to xn, it is also called as joint probability or joint likelihood. Likelihood is the correct term, not the probability. So it's a probability density actually. So probability, a joint likelihood with respect to mu 1, sigma 1 is higher for this data point compared to any other parameter mu 2, sigma 2. So you want to find this mu 1, sigma 1, and for that only we do maximum likelihood estimation. We take this product with unknown parameters, take log of it to so why do we take log? Like, so one reason was it converts it into sum and it makes it easy to differentiate, and the main reason is, let's say you have this curve y equal to x, and y equal to log x will be something like this, just approximating it. So as x increases, log of x also increases monotonically. Okay, so taking this into consideration, we take the log of this product and differentiate with respect to the unknown parameters, say theta 1, theta 2 and so on, and differentiate that the obtained expression, the equate that obtained expression with 0 to find the value of the unknown parameter theta 1, theta 2 and so on. So is it clear to everyone how maximum likelihood estimation is done? And it is generic for all sorts of distribution. It is not limited to any particular distribution. Whatever distribution you want to fit in, you can, given the data points, you can substitute. So you have been given data points, you have a distribution with parameters theta 1, theta 2 up to theta n. You have to substitute this particular data points into the distribution's probability density function or probability mass function, the formula for this distribution in short, and then get the probability values or likelihood values, and then you take the product of this, take log of it and differentiate with this particular law L with respect to each of the unknown parameter and equate them to 0. So this will give you the value of theta 1, this will give you value of theta 2 and so on. Okay, so this is the basic these are the basic steps for estimating parameters for any distribution given the data points using maximum likelihood estimation. Okay, so I hope this is clear, and let us go back to the question. So maximum likelihood estimation is a method to find most likely density function that would have generated the data. So the answer is true. In the context of MLE for normal distribution, select the correct statement. Again, let me start the poll. Don't answer in the chat. In the context of MLE for normal distribution, select the correct statement. The likelihood function depends on mean mu and standard deviation sigma. The values of mean mu and standard deviation sigma that maximize the likelihood function is found. All of the above, none of the above. If you launch the poll, you can answer using the poll. After this, we'll move on to Python notebook, see how it can be solved in Python. Okay, only 3 votes so far. Okay. Fine. Let us see the answer. So answer is all of the above. As we saw, the likelihood function, it depends on the parameters of the distribution. So in the case of normal distribution, the parameters are mean and standard deviation sigma. So yes, it depends on the parameters of the distribution, and likelihood function is nothing but the product of your likelihoods for each of the data points. Then the value of mean mu and standard deviation sigma that maximizes the likelihood function is found. Yes, that's what we do. We differentiate the likelihood function with respect to each of the unknown parameter. In the case of normal distribution, it is mean and sigma standard deviation. We differentiate the likelihood function with respect to mu, with respect to sigma, and then we equate to 0 to find the value of mu and sigma that maximizes the likelihood function. Okay. Which of the following statements about MLE is true? Again, I'll launch a poll. Okay, only 3 people have answered so far. Others, please try to answer. It doesn't matter even if it is wrong. Okay. Yeah, so almost all of you are right. So MLE can be used to estimate the parameters of any statistical model, whether it is normal distribution or Poisson distribution or exponential distribution, binomial distribution, Bernoulli distribution, anything. We just need to know the formula for that particular like distribution, its unknown parameters, and the data points. Okay, which of the following is not a step in the MLE process? Again, I'll start a poll. Okay, only 2 votes. Fine. So the correct answer is calculate the sum of square residuals. So as you saw in the process, first of all, the step is to derive the likelihood function in MLE, which is nothing but the product of the likelihood values for all of the data points. Then we take the derivative of the likelihood function. In general, we take the derivative of the log of the likelihood function, which is known as log likelihood function, for the ease of differentiating it. And then we set the derivative that is taken with respect to each of the unknown parameters of the distribution. So we set the derivatives of the likelihood function to 0 and find the values of the unknown parameters. So the correct answer over here is calculate the sum of square residual. This step is not involved in the MLE process. Okay, so now this is a theoretical question. You may not get such kind of questions in your examination, but this is just to like understand the concept, like in which scenario we use ordinary least square and in which maximum likelihood estimation. So maximum likelihood estimation, as we saw, can be used to estimate the parameters of any statistical model, including linear regression model, which is having these unknown parameters betas, beta naught, beta 1, beta 2, and so on up to beta n in the case of multiple regression. So given the data points, I can definitely estimate the values of betas, like the coefficients, using maximum likelihood estimation. But given an option whether to use OLS, ordinary least square, or maximum likelihood estimation for linear regression, which one will be preferred and when do you prefer it? Any answer? Okay, what do you think? Any guesses, like in what condition, what is the assumption that we have, like when you apply linear regression on any of the data? We just
That it should be a normal distribution. Then we go for OLS.
what should be the normal distribution?
The sampling that we do.
Not really, like there is something. Yeah, that is the correct answer.
Okay.
The error term. which is nothing but the difference between the actual value and the predicted value given the distribution parameters, like the model parameters. So y minus y hat is the error term epsilon, and if you take it for all the data points, ideally that error term should be normally distributed with mean 0, with mean 0 and standard deviation sigma, which may not be the case in real world, like data sets. So in that case you go for maximum likelihood estimation because it is applicable for any type of statistical distribution. So in practice, the choice between MLE and OLS depends on the specific situation and assumptions of the linear regression model. So what is the assumption of linear regression model? That the error terms are normally distributed, and in case if it is not, then you will definitely have to go for MLE. OLS is used because it is simple and more interpretable, because you know that you are fitting a line, you are trying to minimize the errors with respect to each of the data points for the given line. That is like easy to understand, but if the normality condition is not met, like if the errors are not normally distributed, in that case MLE will be the best option or better choice. But if it is the case, like if the errors are normally distributed, then you can go ahead with OLS. Okay, so let us go on to the next problem. Which of the following statement about MLE is true? Let me start a quick poll. MLE always provides the exact solution for the maximum likelihood estimates. MLE always guarantees that the estimated parameters are within a certain range. MLE is not affected by outliers in the data. MLE requires the use of a closed form solution. Okay, for those of you who do not know closed form solution is a solution that can be obtained in a fixed or finite number of steps. Like for example, computing mean of data points. Say you have n data points. So the closed form solution is take the sum of all the n data points, step 1, step 2, divided by the number of data points. This is a closed form solution. So MLE always provides the exact solution for maximum likelihood estimates. MLE always guarantees that the estimated parameters are within a certain range. MLE is not affected by outliers in the data, and MLE requires the use of closed form solution. Okay. So the correct answer is MLE always provides the exact solution for maximum likelihood estimates. Okay, why this is not the case? MLE always guarantees that the estimated parameters are within a certain range, because you do not know the particular range of mean. For in the case of, let's say, normal distribution, you don't know the exact range in which your mean and the standard deviation will lie given the data points. So MLE does not guarantee that, like it will be in a particular range always, although it exactly predicts the distribution parameters given the data points, but it does not give you a range of values in which these particular parameters will may take this particular parameters take. Okay, MLE is not affected by outliers in the data. That is also not true. If we see in the example, let me show it on iPad. So in this case, you see that there is an outlier. Let's say, considering this is an outlier, it is also having certain probability value or probability density value or likelihood value with respect to the data point, with respect to the model or the distribution. which is also getting considered in the likelihood function. So this particular outlier is also contributing to the likelihood function, and if it is too low, like if the outlier values are like too low, this will also decrease this likelihood function value. So in that case, the estimation is getting affected by the outliers as well. So that option was also ruled out. And regarding the closed form solution, so it depends on the problem at hand, the distribution parameters you have. So it's not like always like closed form solution. I won't go too much into the detail, but yeah, you can explore it further later. The likelihood function is a function of mean mu and standard deviation sigma. Is this always true or false? Starting a poll. Please read the question carefully. The likelihood function is a function of mean mu and standard deviation sigma. Is this always true or false? What about the others? I just got 3 votes so far. Okay. Fine, let us see the answer. So the answer is false. It's not always the case. It's only in the case of normal distribution that the likelihood function is a function of mean mu and standard deviation sigma. Okay, let me show it to you on iPad again. So we saw it over here, right? Yeah, please excuse me for this handwriting on iPad. So in this case, when we take the product of each likelihood, like with respect of each data point, you see that this likelihood function L is a function of mean mu and standard deviation sigma in the case of normal distribution. If it were Poisson distribution, it would have been a function of lambda and so on, like it. Okay, sorry, my screen was not shared here on laptop. Yeah, so in the case of normal distribution, the likelihood function L was the function of mean mu and standard deviation sigma, and in the case of Poisson distribution, it was the function of lambda, and in binomial distribution it will be the function of p and so on. So it depends on the probability distribution that you are taking into consideration. Your likelihood function will be the function of the unknown parameters of the distribution. Okay, now coming to logistic regression. Okay, let me just discuss first what logistic regression is, and then we will see some questions and move on to Python notebook. So there was an example given in the lectures on logistic regression. So the problem was like there is a company, and the company wants to give some coupons to its customers, but they don't want to give it to everyone. Like they want to have certain criterion on which they will be giving the coupons, because coupons are also having certain costs associated with them. So what the manager thinks is like they will see the amount the customers have spent on the purchases for over the last 1 year. So the amount spent was one variable, and the second criterion was whether the customer is having credit card or not for that particular company, that company's credit card. So company's credit card. So these were the two criteria based on which they were deciding whether to give coupon or not, gift coupon. So amount spent will be some value, let's say 2000 rupees, 4000 rupees, and so on. Okay, and company's credit card, again it is a categorical variable, yes or no. So well, if we have two categorical variables, how many dummy variables can we use? We just saw answer is 1. So we can use just one dummy variable, it can take value 1 or 0. So company's credit card, if the person is having the credit card, it can be denoted as 0 or 1, otherwise 0, and so on. So based on this data, like the amount spent over last year by the customer, so this is like customer 1, 2, 3, and so on. So the amount spent and whether the person is having credit card, the company's credit card or not, they will decide to give the person coupon or not. Like if they want to give the coupon, they will decide if they want to give the coupon to the person or not. Okay, so this is the problem at hand. But if I want to predict this, in this case this particular variable, dependent variable, is having only two values, 1 and 0. So if you plot this, if only the amount spent is considered, it can be like this. Zero or 1, and the amount is like 1000, 2000, 4000, and so on. So if you fit in a line over here, it may not be the best fit. Okay, so in this case what is done is you try to fit another function called sigmoid function. Let's say the data points are like this. I'm taking only one independent variable into consideration over here in this case. And the sigmoid function kind of looks like this. Okay, and it gives you the probability value between 0 and 1. So for a given amount, say this is like some amount which the person has spent over the last year, I can get the probability of giving the coupon. So this is nothing but probability of giving coupon. So if you see, you can see over here, higher the amount spent by the person, higher the chances of getting the person getting the coupon. Now how is this probability represented? So it is represented using sigmoid function. So this function does anyone know what is the formula for sigmoid function? Anyone? Yeah, one error over here, there, Sharavnan. So it is 1 upon 1 plus e to the power minus x and not plus x, which can also be written as e to the power x upon 1 plus e to the power x, because this is nothing but 1 plus 1 upon e to the power x. So if you simplify this, you will end up getting this. Okay, so this value represents probability. So in the case of logistic regression, what you do, you have multiple independent variables, x1, x2 up to xn, and the dependent variable is taking only two values, 0 and 1. So you can have one linear regression, multiple regression fit on it. Which is not exactly like, we are not trying to do the multiple regression over here, but probability of the variable y being 1 given the values x1, x2 up to xn, it can be given as e to the power, let's say this function is f of x, capital X, where capital X is x1, x2 up to xn. So e to the power f of x upon 1 plus e to the power f of x, which is nothing but 1 upon 1 plus e to the power minus of f of x. Okay, so we are trying to find this parameters beta 1, beta 2, beta 0, beta 1, up to beta n for this particular sigmoid function or logistic function that maximizes the likelihood of each of these data points. Okay, so that can be solved using maximum likelihood estimation, but it will be difficult to do it manually. So that's why we use Python in this case, and we'll see one example using Python. Okay, so this was about logistic regression, why we use it. So let us go back to the slides and see some questions, and then we'll see Python notebook. Okay, let me see how many questions I have. Okay, it looks like there are a lot of questions, so I'll quickly move over these questions. What type of response variable is logistic regression used to model? We saw that response variable in the case of multiple regression is nothing but the dependent variable. So what type of response variable is logistic regression used to model? Answer?
Categorical.
Yeah, that's the correct answer. I hope others got it. So categorical, because it takes only two values here in this case, like whether to give coupon or not, for example, like yes or no. So 0 or 1. Okay. So consider the following statement. In logistic regression, the values on the y-axis of the sigmoid curve can range from minus infinity to plus infinity. True or false? Okay, let me start the quick poll and then answer, because I want everyone to answer. Okay, okay, it's better, like, okay, please answer in the chat directly. Fine. So many of you got it. It's false. The value on the y-axis are nothing but probability values, and probability can never be negative or greater than 1. So it will always be in the range 0 to 1. Okay. In logistic regression, the null hypothesis is similar to what we do in the linear regression or multiple regression. Okay. Fine. So the correct answer is h naught equal to beta equal to 0. It means that the dependent variable, means the variable y is not dependent on any of the independent variables x1, x2, x3. So if the betas are 0, it means that it is constant throughout, like 1 upon 1 plus e to the power minus beta naught. That's it. All the beta 1, beta 2 up to beta n are 0. Okay. So there is a term called G statistic. We'll see that later. I'll skip this question for the time being. Okay, this is also relating to that. Okay, there is one more term called odds. So odds is nothing but probability of event occurring P divided by it probability of the event not occurring. So it is like P divided by 1 minus P. So if it is heads and tails problem, so for an unbiased coin, so what will be the odds of getting heads? Anyone? If it is unbiased coin, what will be the probability of getting heads and probability of getting tails? That's a question.
Probability will be 0.5.
Yeah. So what? Yeah, that's correct. So what will be the odds of getting heads?
1.
Yeah, that's true. It's 0.5 divided by 1 minus 0.5, that is 1. Okay. So and if say for certain thing like certain medical test, like probability of getting a certain disease, getting diagnosed with a certain disease is 0.2. So what's the odds of getting diagnosed with that disease? The probability value is 0.2. So yeah, so the answer is 0.2 by 0.8. Yeah, that's correct. Like it's 0.25. So the odds ratio measures the impact of odds of 1 unit increase in only one of the independent variables. That is true. For the categorical data with n categories, the number of dummy variables will be, we just discussed this, so answer is n minus 1. Suppose you have been given a fair coin. Okay, this is the question, I think I asked it. Which of the following is true? To find out the odds of the getting heads, which of the following is true for such a case? Okay, odds will be 1, we already discussed. The logit function given as L of x is the log of odds function. What could be the range of logit function in the domain x equal to 0 to 1? So the log of odds function, okay, let me just show it to you on iPad quickly. So this is your like odds, and log of odds will be like log of p upon 1 minus p, and this is called as logit function. So what will be the range of logit function given p in the range 0 to 1 inclusive? That is the question. Anyone? Yeah, that's the correct answer. So when p value, the value of p is 0, p upon 1 minus p will be 0, and when the value of p is 1, this will be infinity. So if you see the log function, it looks something like this. So as you tend to 0, it goes to negative infinity, and as you tend towards infinity, it also tends to infinity. So the answer is minus infinity to plus infinity. I hope this is clear to everyone. Log of 0 tends to negative infinity, like as the x over here. So x in this case is nothing but p upon 1 minus p. So as this ratio tends to 0, the log of this x tends to negative infinity, and as x tends to infinity, log of x will also tend to infinity. So the correct answer over here is minus infinity to plus infinity. Okay, G test again. We'll see this in the Python code. So let us quickly go to the Python code. So this was for week 7. Okay, this is for week 8. Yeah. So I have this. So as we do always, import the necessary libraries. We have this file mle.xlsx. For those of you who do not know, all these files can be found in this important data files for each of the weeks. Okay. So we have this data in mle.xl file. We have dependent variable and the independent variable values. So we want to estimate the parameters. We want to fit a line to this data and estimate the parameters of the line, that are beta naught and beta 1. So there are two methods. First is using ordinary least square, and second is maximum likelihood estimation. So in the ordinary least square, what we do generally, we have this independent variable list, we have dependent variable list, we add constant to the list. We saw the reason why we do that in the beginning of this session, and then we pass it on to the OLS model, like ordinary least square model. You'll have to be careful. The dependent variable is passed first, and then the independent variable, and then we fit the model to the data. Okay, so the model is fit over here. Like, let me just run this, and then printing the summary of the model. So you have this R square, adjusted R square. We saw what adjusted R square is. It is taking the number of independent variables into consideration. Then here we have the values of the parameters. This is beta naught and this is beta 1 coefficient, like coefficient of x and the constant term. So for each of this term, you have certain standard error associated with them, and then using that you can compute the t value and the corresponding p value to find out the statistical significance of each of the parameter estimation. And for the overall model, like beta naught plus beta 1x, you have this f statistic, which is nothing but MSR divided by MSE. So higher the f statistic value, higher are the chances of rejecting the null hypothesis given the significance level. Say by default it is 0.05. So higher the f value, f statistic, higher are the chances of rejecting the null hypothesis. Okay, so this was about linear regression, fitting a line using ordinary least square method. And to get the residuals, like the error terms, we have this model which is built on this data. You can use this model.resid resid to get the error terms. Let me just print this error terms once. Okay, and it is having standard deviation of this. Okay, let me just print the mean also. Ideally we should be taking passing this parameter over here to compute the sample standard deviation, but we are just taking the like considering it as a population data parameter. We are uh, passing like no parameter to the particular function. If you don't pass that, it will assume that it is a population data and estimate mu. But if you have that DDOF as set to 1, so the denominator, the degrees of freedom, will be n minus, n is the size or the number of data points you have, minus 1, whatever value you pass. So if it is DDOF equal to k, so your degrees of freedom will be n minus k. So that's the way you can compute sample standard deviation. But let us just see, like assuming it is a population data. So here you can see that the mean is very close to 0, e to the power minus 15, so it is like 0.000 so on, and it's having certain standard deviation 0.6. So it is okay to fit least like linear regression in this case, because the error terms meet the like the assumptions that the mean is 0 and the standard deviation is like some positive value. Okay, so this was using ordinary least square. Now we can use maximum likelihood estimate. So here I have defined this function likelihood, which is having this parameters, slope parameter and the intercept parameter, and these parameters are being passed as the function to the particular likelihood function as parameters. This variable parameters are, it represents the parameters that are being passed to the likelihood, and these are the parameters that we are passing: the slope of the line, the intercept of the line, and the standard deviation of the residuals. Why do we do that? Because we have to find a line that minimizes the distance of each of the data points with respect to that particular line equation, the predictions that we make with respect to line equation. So here, as we saw in the theoretical part of it, we are trying to like minimize the likelihood function given the data points. So the data points are given to us x sorry, x. So x is like I'm taking x over here from the Excel file and trying to we want to minimize this particular likelihood function. So why this particular formula over here? You will get this when you take the derivative of the likelihood function and differentiate equate it to 0. Sorry, this is just the likelihood function, and what we want to do is take the derivative of it and with respect to each of the unknown parameter and equate them to 0 to get the value of unknown parameter. And for that you can use this function called minimize. Actually it is trying to minimize the negative of the likelihood internally, as far as I can understand, because we try to maximize this likelihood function. So professor has used this function minimize. So maximizing L is equivalent to minimizing the negative of that particular value. Herein, so this minimize is there in scipy.optimize package. So optimize, so it is like one of the it uses multiple optimization algorithms internally, which we don't need to know exactly, but for your information, here the method that is being used is this LBFGSB. Okay, let me just show you the full form of this. It is a limited memory Broyden, Fletcher, Goldfarb, Shannon, very crazy name, but yeah, so that's the name of the algorithm. You need not know the details of this algorithm, but this is one of the optimization algorithms that is being used in the minimize function to find out the parameters of the distribution or the statistical model. In our case, it is a line with two parameters, beta naught and beta 1. So we are having a likelihood function. We are passing the initial guesses of this particular parameters, beta naught, beta 1 and the error of the residuals, and passing this method name. This was used by Professor Ramesh, so I am using it as it is over here. So let me just run this. So you can see that the beta naught, beta 1 and the error term over here are exactly the same as beta naught, beta 1 and the standard deviation of the error term that we found using ordinary least square. So this was to show that whatever we can find using OLS can also be found using MLE, and MLE is like a more general way to find the unknown parameters of any sort of distribution given the data points. So you will have to define this likelihood function accordingly for each of the distribution into consideration. Like the parameters will also change and the likelihood function will also change accordingly, and you will have to pass that likelihood function to this minimize function with the initial guesses of the parameters and the method you want to use. So you can refer to the documentation of this minimize and check it for different sort of distributions. And here is the same code written in a better way, like I have vectorized this function. So this is just for your information, like you always, like you need not write this long formula over here. It can be written in a very short form using the NumPy library. I'll leave it to you, you can explore it later in so it's already 8 o'clock, so I'll just keep that part. And then there is this logistic regression problem. So as we discussed in one of our examples, we had some customers, we had the data of their spendings or purchases they made in the last 1 year. We have this data whether they have the credit card of the company or not, and then the data that company has given them, like whether they have used the coupons or not. Like company has given them coupons, we saw that variable as whether to give the coupon or not. Here it is like whether the person has used the, in the training data it is like whether the person has used the coupon or not. Okay, so here is just a scatter plot of coupon being used and the spending over here. So what we are doing over here, similar to the linear regression or multiple regression, we are having this data points, spendings and the card. Here it is already 1 and 0. If it is not 1 and 0, if it is categorical in nature like yes, no and so on, so you will have to convert it first to the numerical values using dummy variables and pass those variables over here. So here it is only yes, no, so it's 1 and 0. If it were like yes, no, maybe, so in that case you will have to have like this 1 0 0 1 and 0 0, and you will have to pass in 3 variables in this case, like spending, x0, x1 sort of, and the dependent variable is coupon being used or not. What similar to what we did in the linear regression, we are adding constant for the intercept term. Now this is the main thing. Instead of sm.ols as we were doing over here, we are using for the logistic regression problem, we are using sm.logit and passing the dependent variable and the independent variable. So let me just run this. So you will see some different terms. Yeah, so these are the same, like for coefficient of card is 1.09, coefficient like this is like beta naught, beta 1, beta 2. So you are trying to find the coefficients. Each of these coefficient is having certain standard error associated with them. So in this case we do z-test. One assumption in logistic regression is that you have sufficient number of data points to estimate these parameters. You kind of need like large number of data points to correctly predict the model parameters. So in that case z-test is applicable, like you can use z test instead of t test. So this z test that you are using is like the z value is being computed using the coefficient like divided by its standard error, and for the given z value you will be having certain p value. Based on that you will decide like whether the particular coefficient or variable is significant or not in deciding whether the person has used coupon or not. Okay, so this was the case, and this particular test to find out the statistical significance of individual variable over here, the coefficient of individual variable, for coefficient of individual variable, it is called as wall test. So you might get some questions like this, like which test is used to find out the statistical significance of individual variables in the case of logistic regression. So the answer is wall test, WLT. And similar to the R square term that you saw in the case of linear regression, in the case of logistic regression we have this pseudo R square. It's not exactly R square, but it is used to show the variability that is getting captured by the logistic regression model. So there are multiple details associated with it, and there is a nice channel, like I will also put link in the chat box, like description of the video. Like if you would have seen, like in the description of my video, I am having these links over here for these channels. So one of these channels is StatQuest. So there is a very good playlist on machine learning. In that you can go to the linear regression or logistic regression part of it. Let me just go over there.
Hello, I'm
So I would recommend like you go and look into the logistic regression on this particular. So here it is, playlist. So just go over this logistic regression videos, and you will get to know the details about how this pseudo R squares and other terms are computed. So as we saw in the case of linear regression, there was this F statistic that was being computed to identify quantify the statistical significance of the overall model. Similarly, in the case of logistic regression, we have a G test, and to compute the G statistic we use this formula, negative 2 times the log of L null, it is LL null actually, divided by LL LLR. So what is LL null and LLR? It is log likelihood score for the null model. And what is null model? When we don't take the independent variable into consideration. And LLR is log likelihood with respect to regression model. So sorry, this one particular value over here, log likelihood with respect to the regression model, and log likelihood with respect to the null model without taking which takes no independent variable into consideration. So the ratio of this particular ratio is called as G statistic, and it follows a chi-square distribution. So given the G value, you can compute the corresponding. So let us compute the G value using the LL and LL null over here. So we have this G value computed, and we can compute the P value using 1 minus chi-square distribution. Chi2 is nothing but chi-square distribution. For norm, we use norm.cdf, normal distribution. For chi-square distribution, we use chi2.cdf. We have to pass this G statistic, and this G statistic will be having the degree of freedom equal to the number of independent variables we have in our model. In this case, we have 2 independent variables, spending and card. So you will have to pass on that independent variable and compute the P value, and you can see that this P value is less than 0.05, which means that the overall model is statistically significant. And you can see the same P value computed over here in the summary, LLR P value 0.0010. Okay. So coming to these questions, like I had a few questions on G statistic and all. So G statistic in logistic regression is negative 2 times ln of likelihood without variable and likelihood with variable. If you just simplify this, it will be likelihood log of likelihood with respect to variable. Like if you take this negative term inside, ln of likelihood with respect to variable divided by likelihood without variable. It is equivalent to MSR divided by MSE. It is equivalent, not the same, to what we do in the case of linear regression, to compute the F statistic. So similar way, similar intuition can be applied over here to compute the G statistic. Which of the following is true in the context of logistic regression? Okay, quickly answer this and then we'll stop. In exam coding questions, it depends, Neha. I'm not very sure like how many coding questions will be there, but coding questions in the sense they will be giving you the snippet of the code and asking you like what will be the output of the code, or like giving some blank parts in the code and then will be asking you to select the option which does the correct operation for the given code. So kind of that questions might come into examination. You won't have to, as far as I know, they won't be asking you to write a Python code and run it over there, but it will be mostly MCQ based questions. Yeah, but still do confirm with the team. Like I'm not a part of NPTEL team, like a regular team who handles all these logistics, but yeah, do confirm it on the discussion forum. So many of you answered D. So yes, that is true. So wall test is used to check the individual significance of the independent variable, and G statistic is used to check the overall significance of the model. So this was just interchanged over here. So the answer is none of the above. So this also we saw. So G test, if the null hypothesis is true, the sampling distribution of G follows a chi-square distribution with degree of freedom equal to, we saw the answer also. I'll stop it over here, number of independent variables. Okay, so this was all about maximum likelihood estimation and logistic regression, and I hope you learned something from this session. Please let me know if you have any queries. We can discuss it during the next session. It will be on Friday next week, although it is a holiday, public holiday, but yeah, we'll be having the session. So thank you everyone for joining. I'll end the session now. Please let me know if you have any queries.
Thank you for the session.
Thank you. Thank you for joining.